Hongxun. What's your name? Oh, okay. Chen Jun team. Team 5? All right, let's go ahead and start. Well, with all you knowing, without you knowing, it's time for the second exam, which is coming up next week, exactly Thursday this time. The format and the process will be identical. If there will be any other changes, they will be posted in channel exam 2. All right, so stay tuned. Now, in case you have any questions, feel free to post there as well. Okay. In the outline today, let me just bring up the slides, which is not happening. So let me. Put this down and bring up the slides here. Okay, so this is where we left off the DNS. And in fact, last time we went through quite a bit of DNS already, right? So we learned about the architecture, where the communication mode is client server. So there will be machines, okay, that are resourceful somewhere in the center of the internet, the core of the internet. And the clients are us, okay, using World Wide Web, using email, trying to find name to IP address translation, okay, or email service to mail server IP translation. So client server mode. And we know that the DNS server, okay, there's a huge structure behind. It's essentially a distributed database of all these mapping entries. Okay, lots of them. There are so many of them, so they're actually distributed among physical machines around the internet. And they are structured this way, hierarchical. So at the top, we have the root. The second level, the top level domain DNS server. And at the bottom, what's that? Authoritative DNS server, the one that is the hardest to pronounce. All right. Oh, but there's also what? Local DNS server. What is that? That one actually looks a little bit like the proxy web server, isn't it? It's very close to the client. And usually an ISP or an institute sets up a local DNS server, just like ISP Institute set up a proxy web server. So architecture, nice features, being distributed and hierarchical. Now this is actually, we heard it many times, okay? Client server, nothing new. Now we also talk about how we exchange these DNS query and reply messages, okay? From the client to the local DNS server, from the local DNS server to top level domain, and then authoritative, and then back to the client, right? So there are two different models, okay, two different modes to exchange these messages. So we do have two exchange modes. The one that is being used more today is called the iterative, which is bypassing the root, okay, and making sure that the root server has the lightest load possible. Now, what about the message format, right? So I think I mentioned at the beginning of chapter 2, for each application layer protocol, we care about the architecture, the service model, as well as the message, right? How we exchange them. When you receive a particular message, what does the server do next, or what does the client do next? We also care about the formats, okay? Exactly what's in these messages. So we'll start from the format, okay? But before we talk about the format, we need to talk about, what are these mapping entries in the database? Because after all, these are the content we are looking forward to retrieve, okay, from the DNS service. And then lastly, we talk about the underlying service this application layer protocol will be using. This is related to what? The quality of service that people are looking for, okay, for this particular service. Okay. So is it TCP or is it UDP we are using? Would you like to guess which one for DNS? Hey, guys online, feel free to take a guess. DNS, whether it's using TCP or UDP. We'll come back to that later. The fact is that I think the textbook didn't even mention whether it's TCP or UDP, but it's kind of important. So we'll discuss this briefly, okay, at the end of DNS. And so let's go ahead and start from database entries and then move on to the messages. So this is what the entry look like. Very simple. Okay, it's a tuple of 4 entries, 4 values. The first value is called the name, second value, type, and TTL. If you recall the last slide, last week, is it? Okay, it feels like ages. It was last week. Okay, Tuesday last week. Right, we talk about, the top level domain server's IP is cached at the local DNS server, isn't it? So this way, the local DNS server doesn't need to go to the root at all. But that cache entry will only be in the local DNS server for some time. Okay, and that time is defined by this value, TTL. So this defines how long this entry will stay on the local cache, local DNS server. So it might differ from entry to entry. Now, name and value, very straightforward. What does DNS do? It's providing the IP address if someone is looking for the IP address for a host name. So this is the host name, and this is the IP address. Okay. What's slightly complicated that we did not mention yet is, host name to IP address mapping, that is the very basic type of these entries in the database. So this is called the A type, okay. How trivial, starting from A, right, and B, C, D, E, F. So A, no, it's not exactly A, B, C, D, it's actually saying address. Okay, so this is the entry for us to find the IP address. So name will be host name, value will be IP address. If it's a name to IP address mapping, type here will be capital A. Time to live could be 2 days, or 24 hours, or 10 hours. All right, so now you get a better picture of all the records being stored in the distributed database there. Now, each of these entries, there's a formal name called the RR, resource record. Okay, so the database stores these RR entries. Now, there are 3 other types of entries. Okay. So one is called this, MX. This is for someone to find who's the mail server for a particular domain. Have you wondered, right? We're writing emails to, for example, poly.huang@ntu.edu.tw. So who's the mail server of ntu.edu.tw? You know what? DNS also help, okay? The sending email server, if you recall SMTP, the sending email server is the client of SMTP. Sending email server will need to query DNS service first to find the MX entry for that domain, okay, that your friend is staying in. If you have a gmail.com email address, and if I'm writing to Samuel's gmail.com email address, so my mail reader or writer there would actually try to find what is the mail server of gmail.com, which is smtp.gmail.com first. And then my local DNS server will then look up again to look up to gmail.com authoritative DNS server to find the IP address. So to send an email, I first fetch this entry, okay, and then fetch this entry in Gmail's authoritative DNS server. Okay, so there's quite a bit of thing going on there, just trying to get the IP address of the mail server. And then the NS entry. Let me describe what it is, and then you guess why this is necessary. Name is the domain, such as ntu.edu.tw. Okay, so that is the domain, the entire NTU. So NTU's web server is www.ntu.edu.tw. NTU's mail server, very straightforward, mail.ntu.edu.tw, but it's using a strange port number, 993. Okay, it's not using the 25 port number. Okay, I guess they want to prevent attacks. Okay, but no, someone just do port scanning, then quickly hacked, and we discovered that NTU is using the Microsoft Exchange as the server, and there are so many exploits. And therefore, you guys now have the g.ntu.edu.tw email address. Okay, because this guy here is not very reliable. All right, so hey, name is the domain, and value is the host name of the authoritative DNS server. Why do we need such an entry? Well, if my local DNS server is actually asking for Gmail's mail server, right? And if my local DNS server doesn't have a cache entry of where the authoritative server of gmail.com is, what does my local DNS server do? Well, it asks the top-level domain server first, right? To find the authoritative DNS server of gmail.com. And so the top-level domain server is therefore returning what? This. For gmail.com, smtp.gmail.com is the mail server. Mm-hmm. Oh, sorry. This is gmail.com, and this is the authoritative DNS server for gmail.com. Okay, so excuse me. So this is the entry stored in top-level domain DNS server. Okay, so in the TLD servers, lots of these entries. Amazon.com, and then the host name of the Amazon.com's authoritative DNS servers. Now this one is for the canonical name mapping. www.google.com could be actually The physical machine could be a different name. Just like www.ibm.com, this is actually easy for us to try to find, but the actual server, okay, providing the content for this URL could be this guy. Server is.backup2.ibm.com. So this is the real host name. And this is the nickname. Okay, and this is the one that's a little bit easier for human beings to memorize. Okay. And this is necessary these days because to provide content for a large website, nowadays we use many physical machines. And different physical machines, we need to give them different names. Otherwise, we'll confuse who's who. Okay. So the name part is the nickname. And the value part is the canonical name, the actual name. Okay. All right, so there are these major types of entries. So between the various DNS servers, these messages being exchanged are all in this format. Okay. The direction sending the query, okay, is coming from the client, okay, all the way down to the authoritative DNS server. And then replies will be coming back the other direction. Okay. What's really interesting for DNS is that no matter which type of messages is, the format is the same. Okay, all look like this. The way to differentiate whether this is a query message or a reply message, it's done by using a different flag. Okay, so flag here, you might have a bit there, 0 indicating it's query, 1 indicating it's a reply. There are potentially other flags, whether the reply is coming from the authoritative DNS server. And then there's this identifier. This is for the local DNS server to try to correspond. For this query, this is the reply. Okay. So this is the format. And here you see number of questions. So in a query, we could actually, in a query message, we can actually ask multiple questions. Okay. In a reply, one can also provide multiple answers. So you can imagine the local DNS server there asking several answers at the same time if it's all going to the same TLD server. Similarly, TLD could be replying, okay, multiple answers in one message, okay, for different queries earlier. So this is counting the number of questions and answers, counting the number of authoritative RRs, and additional, none of these other types of RRs. And then questions, the detail here. Answers, detail here. Okay, and they'll be counted by this value. These will be counted by this value, and these will be counted by this value. All right, so as I mentioned, these are counting the entries. So number of questions counts the entries here. So in a question, you provide a name, right? Of course, the value part will be empty because value is what you're looking for from the database. But answer here, then you see the full RR, okay, showing in each of the entry here. And this is records from, or RRs from the authoritative servers. And these are all the additional information. So that was the format. Okay. It's actually a lot more straightforward than HTTP, response and request, right? Now, this is to be practical. Okay? If you are starting a company, creating your own domain, let's use an example. So if you're starting a company called Network Utopia, what do you need to do to make sure that your web server and your mail server will be up for service? So other people interested in your company, interested in the service you provide, need to get the IP address of your web server, isn't it? How? How do you ensure all your customers, potential customers, okay, get the networkutopia.com's IP address? Step number one, because these customers, local DNS server will be asking who first? The TLD DNS server, right? So you need to insert an entry to the TLD DNS server. Saying what? Oh, saying I'm a new domain, networkutopia.com. Okay, and I have already set up an authoritative DNS server, which is right here. This is the name of the authoritative DNS server, and this is the IP address. Okay, so essentially, you register 2 RRs into the .com TLD server. The first entry, the domain name, right? And then the authoritative DNS server's host name. And this will be what? The NS entry, isn't it? We talked about it. In the TLD DNS server, there are lots of these NS entries. There needs to be also the IP address of the authoritative DNS server. And this is an A entry, okay, in the TLD. So in a way, when your local DNS server sends query to get, what is the authoritative DNS server's name of a domain, this RR will be returned first. And then the local DNS server sends to the TLD server and find out what is the IP address. So this entry will be in the second exchange. But nowadays, you can imagine the TLD server optimize things as well. In that reply, sending both entries. Because the next action the local DNS server does is just simply sending query to the 212.212.212.1 to find out what is the IP address of .networkutopia.com. But in order for DNS1.networkutopia.com to return, okay, to your local DNS server's query, you also need to add 2 entries, okay, in your DNS1.networkutopia.com. One is the A-type record that provides the IP address of this host. The other is the MX entry. That is the host name, the mail server of your domain. And of course, the IP to the mail server host names entry. So there'll be an MX record as well as another A record. So these are the things you need to do in order to create a domain. You need to register, okay, to the TLD server. And TLD servers are maintained by these non-profit organizations, if you recall. .com is supported by Network Solution. I think for Taiwan, it's TWNIC, I recall. So if you want to register something .tw, contact this institution, TWNIC. And then you need to set up a DNS server locally in your company. You need to set up a web server. You need to set up a mail server. Now, DNS server, authoritative DNS server, the mail server and the web server, they don't need to be separate physical machines. They can be just software running on one physical machine, which is somewhat powerful. Otherwise, it can be very much loaded. And DNS is often the target of attacks these days. Okay. To the left, DDoS attack to the servers. Okay. For example, root servers being bombarded by queries. So that is really bad. But nowadays, it's not so successful because the root servers are not expecting a lot of traffic. So they can just filter traffic. Okay? If there is a certain IP address continuing sending queries, then they can block queries for a while. And this is fine because after getting the top domain level DNS servers, local DNS servers always cache the TLD. So they are not expecting someone querying the TLD server again and again and again in a short time. Okay. All right. And what about bombarding the TLD server? Yeah, this one is a little bit more dangerous, but okay, local DNS server also cache the TLD IP addresses. So we don't have to worry too much. The same strategy being used by the root server can be applied here. We just filter traffic. If someone continues to probe in a high frequency, block that IP address. Now, these are not good, but these are harder to pull off. Okay, what about, okay, we try to cut in the middle of the path between your local DNS server to the, for example, TLD server, and intercept all your queries and not forwarding it to the TLD, so you will not be getting any responses at all. Okay, that way, you won't be able to do any internet services, not being able to find the web pages you're looking for, not being able to send emails that you need to do. But this is hard to do because the requirement is that the hacker, okay, finds a way to intercept your queries. So that hacker needs to be physically somewhere, okay, along the path between you and the TLD server or the authoritative server. So usually this type of attack is done by, for example, to bring down NTU's authoritative DNS server, go somewhere sitting in Jizong, okay, and then explore the network a little bit and find where you can do that. Okay, so usually it's from insider. Okay. DNS poisoning, now that is evil. Okay, so this is a little bit innocent. We just cut you off from your service. But this is actually trying to bring traffic. Okay, for example, if someone wants to access their bank account, okay, and we inject an entry pretending that my IP address is the bank server instead of the legitimate one. So send bogus replies to the local DNS server. The local DNS server will then send your bank locking messages to my machine. Then I get to harvest your username, password, etc. But you see, this one is just as hard as the man-in-the-middle attack because you need to be able to intercept and send bogus reply. Exploit DNS for DDoS. Although we talked about this already. Okay, pretend to be. You send queries pretending to be someone else. So we spoof the source address, because that way DNS would be sending replies, okay, to the target of your attack. Okay, so this was done before. Okay, but now we know how to prevent this. Again, to limit the rate of sending the queries. And that takes us to the first quiz today. Okay, so this quiz, okay, so this one is a little bit intensive. Some of you might have seen this on the Slack. So quiz number 10. This one is very open, very, very open. Okay, I don't know if the idea came up to you anytime, okay? So it's time to get real, okay, you decide. This is enough college education for you, all right? So English as the interface for lectures is too hard for me, okay? Okay, or pollys video is a little bit too slow, okay? Can we go a little bit faster, okay? You decide that you're not learning fast enough, okay, or deep enough, and you decided that, hey, let's just get real. How about that I start a company now today? And Petbook is totally better, okay, than Facebook, okay, or IG. So it's a social net for pet animal lovers. So you use your favorite pet's picture as the profile picture, okay, and this is gonna grow bigger than Facebook. Okay, so this is the cat you hear in the video meowing, okay. And now the challenge is here. So this is a very small startup, okay? You are your own CTO in addition to being the CEO and CFO and COO. Now you need to try to structure, okay, your Petbook server, okay, and direct pet page query. So the server load is balanced and the delay is low. Okay. So I ask you, would you prefer modeling your server network for Petbook more like DNS or SMTP or HTTP? Okay, so HTTP, the basic version, as well as the version with the proxy server. Okay, so any of these will be fine. Or better yet, you want to come up with something that's kind of a hybrid of the techniques being used in any of these server network. All right. As a hint, let me show this. Okay, this is also kind of a review. HTTP, how does it work? Client sends request to server, server sends reply. Structure, very simple, there's just one server. With the proxy, then you have something in the middle here. What about SMTP network? Well, it looks like this, right? The client, where the reader is, the email reader is, connects to the local mail server, which is the sending side of the SMTP protocol. Server is the receiving side, okay, server. So email gets pushed this direction. Oh, how different these structures are. You see, the local side. Oops, okay. Okay, I'll come back to that. So let me go over the DNS again. DNS next. So DNS, you see, server here gets expanded to hierarchical. So from HTTP to email, you see the local side being expanded. There's some sort of proxy, okay, or representative here, collecting all the emails from the local area and then send all the emails at once. And then here we see from email to DNS, we're expanding the server side, okay, of the architecture. So from just one single server, we now have a hierarchy of these servers. So we could redirect the loads or balance the loads somehow. Okay. Good. So with that said, let's find your teammates. Okay. Think about structuring Pepbook server network. And guys online, how is the streaming quality today? Okay, let me know. Should be working. Ah, I see. Okay, that's a good point. That's a good point. So maybe I can add some animations so that you see in the animation, okay, what I'm stressing. Okay, thank you for the suggestion, Yuanxiang. A little. It is a little. Okay, now, who's gonna go first? Which team is gonna go first? You get extra credit, okay, if you go first today. Yeah, maybe I should check Slack. Some of the teams might have already. Let me check Slack. Slack here. Oh, all right. Quiz 10. Oh, Kevin? Kevin Yao, right here. Team 15, you guys? Okay, so Kevin here prefers modeling the as a combination of SMTP and DNS. Using SMTP when we have to send direct messages with our pet friends. Oh, interesting. Interesting. Yeah, because between the SMTP servers, it's kind of P2P, right? There's no hierarchy. It's flat. And you don't have to worry about balancing load if you are sending direct messages, right? Just between you and your friend. But using the DNS network structure for connecting those friends' pet pages. Ah, okay. So the pages of your friends will be distributed, okay, across multiple servers. I see. Ah, okay. I understand. Okay, so you are designing the pet book seriously. Okay, so so it's like Facebook. There's a messenger there. I see. Okay, I did not. Well, okay. Good job. Good job. Okay, this is an extended pet book service. All right. All right. Wow. Okay, so they're already designing multiple functions to the pet book. And Junting, I hope I'm pronouncing it right. Right? No. Team 1, Junting, maybe. Is that right? Okay, good. Team 1 is saying, data, lots of different use. Okay. We don't actually need a hierarchical structure to search from one user to another. Therefore, using an SMTP, okay. Okay. So maybe this is what Facebook did also at the beginning, right? Until there are actually very diverse people. Otherwise, you really don't need that complicated structure like DNS. Keep in mind, DNS, the reason that it has so elaborated structure because for every service we're looking for on the internet, it goes first to the DNS servers and back. And there are so many of us using it. So that's why you see this very elaborated structure in DNS. So Junting here, you guys should start a company, okay? Because your design is very cost effective. So you need to sustain the growing period, right, before you expand. Lin Boshun, I guess. Boshun, you guys? We will combine DNS and HTTP proxy server. This is because we need DNS to query the IP address first, and then use HTTP to query the data. Oh, okay. Interesting. Interesting. Okay. Good. So you use DNS to get the IP addresses of the server first, and then use a simple HTTP query reply to get your fence book. Okay, so you're thinking slightly differently, but that should make sure the operation goes smooth. So you're thinking a little bit more like Junting. It's flash service. Jingyuan, okay, so this is the online group, Team 2. Yeah, I did notice Team 2 prefer to stay in lab. Okay, that's a cow. In the lab or in the dorm. Okay, that's... Use HTTP first when the company is small, all right. And there are few users, which can save a lot of server cost, yeah. Then with the increase of users, the company gradually become rich and then change to SMTP. Oh, interesting, interesting. Now, if Petbook is a big success, then eventually you move to something like DNS, okay. Okay, so you are incrementally introducing slightly more complicated structure for the database you have. So Petbook, with all these entries you are actually editing or inputting into the system, it's also a huge distributed database, isn't it? Huge distributed database. Okay, all right. Okay, so now you guys get the rough idea, okay? How to design your own application, okay? Internet applications. Good. Now let's move back to the lecture. Oops, sorry. I did not intend to do this. So that was pretty much the end of DNS. But we do have this to talk about. Now I'm going to take a poll. Okay, those guys online, you guys can also guess. Those who say DNS use TCP as the underlying service, raise your hand. All right, supporters, 1, 2, 3, 4, 5, 6, 7. All right, let me see how many are online. Okay, no one is. Okay, there's a slight delay there, so they are probably keying it in. So 7 here in the class, supporting TCP. What about UDP? Those who say, I'm going to go for UDP, raise your hand. 1. Okay, less enthusiasm. 1, 2, 3, 4, 5. Oh, okay. 7 against 5. TCP wins. But DNS is using UDP, okay, as the underlying service. Why? Because which one we choose depends on the quality of service we need to provide. So if we click on a link to go to a web page, do you expect that there's a TCP connection establishment first, and then you send query and then reply in case there's a packet loss? In chapter 3, you will hear. There'll be some wait time until retransmission. UDP is used by DNS for a very simple reason: fast. Fast, simple, fast. So the way that we recover from potential DNS query loss or DNS reply loss is simply send it again. So local DNS server would just say, after some millisecond of time, if no reply, ask again. And that takes us to the next topic, P2P file sharing, okay? Or P2P applications. So in this part, we're going to go through 3 specific topics. First is an overview to give you a nutshell how P2P-based applications look like. And then we'll walk through a few slides just so that you're convinced there's need of P2P-based architecture as opposed to always client-server. And then towards the end, you will hear 2 examples. One is BitTorrent, the other is Skype. Oh, whoops, sorry, go back. Okay, the nutshell is simply this. There's no longer always-on servers. No more servers. Okay. Servers are also the expensive machines, so you can imagine one reason that people started using P2P-based architecture. One is to cut down the cost. But then, arbitrary end systems like this, the car, the laptop, the PCs, can all now establish connection to each other, so the communication is actually direct. There's no server involved. But the thing is this, hey, this card is moving around, so its connectivity could go bad and good and bad and good. And the IP address could change, right, from this domain to this other domain. So the connectivity there, unfortunately, is intermittent. Okay, so 2 key features: no server, and the connectivity of these entities, these end systems, or we call it more formally, peers, are very loosely connected, intermittently connected. They go on and off and on and off. And it's hard to expect who's going to be on and who's going to go off next. So that's P2P-based architecture. So essentially, clients talking directly to clients. No more servers. But why? Okay, let's think about this problem of transmitting a file. Okay, so consider this scenario. We do have a file server here, hard disk storing all these files. Let's suppose there's a file size big F, and we need to supply the file to each of these users, each of these clients. Okay. So this is the client-server mode transmission. Now let's assume that the server's uplink capacity, so server upload capacity is US, U for upload. And all these clients, there are N of them, each has an uplink capacity and downlink capacity, or upload, download capacity. So this is DI for user I, or client I, UI for client I's upload capacity, and DI for client I's download capacity. Right. So let me ask you, how much time it will take to distribute this file, size F, from this server to all the peers? Okay, let's calculate, right? Let's calculate. So first of all, the server will need to what? Upload the file. How many times? N times and sequentially, right? Because each of them will establish a TCP connection and then let the file go to the client. So there'll be N copies of the file, NF divided by the upload capacity of the server. Okay. But it can also be the case where the download capacity of a client being so low, so low such that NF divided by US is still smaller. So that is the worst case. Let's assume that the very, very low download capacity is D min. Okay? And so to download the file, one file to that client is F divided by D min. So the total transmission time, okay, is really the maximum of either two. So this is the server upload time, and this is the worst case client download time. Okay, how do you like this? Which part you think is the one limiting or holding the transmission time up? Yeah, it's this one here, because there's a factor of n here. If there are more clients, then potentially this term can go higher and higher and higher. Okay. Now this can only go small to some degree. So having this term here is essentially saying that the file download time will go linearly, okay, to the number of clients you have. Oops, sorry, it's time already. Okay. So that's quite a day now, and we'll continue. So this is just the client-server modes download time. Next Tuesday, we'll start from the download time for the peer-to-peer mode. Oh, okay, we have supporters for UDP and TCP. But one vote each, so TCP still win. There are hands. Okay, so I guess. Yeah, hand means, so I guess Jingyuan is voting for TCP, but I'm not quite sure it's Shi Wei. It really depends on when did you raise the hand. All right, good. So I'm gonna just close the stream. Okay, now I'll see you Tuesday next week. Sure. Oops, about the term, yeah.
Why not just adding them
together?
Yeah.
Ah, good question. You see, it could happen, right? So one of these N copies might finish uploading, and this guy is downloading at the same time while the server is still uploading other files.
So
it's a little bit complicated.
Maybe I sequentially send to here, and here.
Yeah.
And maybe I finish sending this client, but this client is still downloading.
Yeah.
Oh, okay.
Or the server is still uploading. Yeah. Yeah, so it's a little bit tricky. And this is a little bit safer, write it this way. Although I don't think the difference is all that big.
Oh, yeah.
Okay. What's your name? Chen Junting. Oh, okay. I asked you already. Yeah.